Hi, this is my introductory video to proton NMR. So hopefully you've done the carbon-13 NMR, that will help you out. So proton NMR is all about hydrogens. So when we say proton, we really mean a hydrogen atom in this case. So it's a really very powerful analytical technique, tells you lots and lots about your organic molecule. So I'm not going to tell you how it works. If you're interested in that, you can go away and find out. It will probably help your understanding, but for the exam, it's not required. The spectra themselves look quite dull. So essentially you have a line at the bottom and then some lines going up. And at the bottom, you've got a scale which runs backwards, as it were, from 0 to about 10, and you have this little lowercase delta symbol, and then it will say ppm. So that's chemical shift is this symbol here. That's what that means in ppm, which is parts per million. So essentially you're looking at how shifted each line is compared to this line at 0. So they sometimes draw this peak in, they sometimes don't. This is a reference peak, so every time they run an NMR spectra they have to put a reference substance in, and the reference substance is tetramethylsilane, TMS it's often shortened to. So this is your reference, and we look at how shifted all the other peaks are compared to them, which give them a chemical shift value which we can use to interpret our spectra. Okay, so when you look, you might see that some lines look a little bit thicker than others, and we'll talk about why later. But that's our spectra. So what can we find out from it? Actually, a lot. So there are 4 different things that we would look at. So the first thing, nice and straightforward, is we would look at the number of peaks, and that's easy to do. So you don't count the one at 0, and other than that you just count how many peaks there are, and that tells me the number of hydrogen environments. And when you're answering exam questions, make sure that you link these 2 things. So if you were looking at a spectra and they were writing about it, you would say there are 3 peaks because there are 3 hydrogen environments. So make the link in your answers. So that's nice and straightforward. We'll come back and do some examples. The second thing I can look at is the position of the peaks, okay, i.e. their chemical shift values. So where are they on that scale? And that will tell me the type of proton. Right, so that tells me the type of the proton, and I can find that out from looking at my data sheet. And again, we'll come back and have a look at this. So you can look at your data sheet. In terms of the order that I would look at these things, actually, if I'm interpreting the spectra, personally, I tend to look at the chemical shift values last, because there's some kind of variation in where the peaks can appear. So we need to know that we can do it, and sometimes they ask you specifically to do it, but personally, if I'm given free rein, it's what I would look at last. The third thing that we could look at is essentially, I'm going to write the height of the peaks, but that's a bit of a kind of lazy shorthand. That's what we usually do, but that's not how we're supposed to phrase it. So you look at the height of the peaks. Really, we're supposed to look at the ratio of the peak areas. Right, so we should look at the ratio of the peak areas. So is the ratio 3:2 or 3:1 or 6:1? In practice, a lot of the time the peaks are very narrow, so their area is essentially the same as their height, which is why usually we often just look at the height of the peaks. Okay, but strictly speaking, it should be the ratio of the peak areas. And really that tells me the ratio of the number of hydrogens in each environment. And again, we'll come back and look at some examples of this, and then it will make hopefully a bit more sense. But what we're saying is, if the ratio of the peak areas, or their heights if they're very narrow, is 3 to 2, then the ratio of the hydrogens is 3 to 2. If I've got a ratio of 3 to 1, I have to be a bit careful. I know the ratio of hydrogens is 3 to 1, but is it 3 to 1 or is it 6 to 2? Okay, so strictly speaking, it's a ratio. And then the fourth thing, which I'm going to cover in another video, so we're not going to do that today, is I can look at the splitting pattern. So what happens is some of the peaks, if you can zoom in on them, which they can in high resolution NMR, are actually, rather than just being one peak, they're split into multiple peaks in a specific pattern. And the splitting pattern tells you about the number of hydrogens on the next door, that was easier for me to spell than neighbouring, on the next door carbons. Right, so the number of hydrogens on the next door carbons. So you can actually tell what's next along either side. If it's got hydrogens on, you can tell how many hydrogens there are on the carbon next door, which makes this such a powerful technique. So those are the four things that we need to know. Let's look at some examples to help us understand a bit better. If you've done carbon 13 NMR already, then this should be slightly easier. Right, so let's look at, I don't know, just making this up. Apparently we're going to look at butan 2-ol. Okay, and this is where I have to actually draw in my hydrogens instead of being lazy. So we're looking for how many hydrogen environments. Something to remember is all hydrogens on the same carbon are in the same environment. So it's like if you've got people in a room, all the people in the same room are in the same environment. So all of these three hydrogens are in one environment. This hydrogen on the OH isn't like any of the other hydrogens at all. It's not similar, it's attached to different things with different neighbours. So that's another environment. This hydrogen, again, is different from all the rest, so that's its own environment. These two are different from all the rest because of what's around them, but they are the same as each other, so that's another environment. And these three are the same as each other, and they're different from these three because this CH3 is next to a CH2, which then goes on to a CHOH, whereas this CH3 is directly next to a CHOH. So they're not the same environment. They've got different things next to them. So in this one, I've got 1, 2, 3, 4, 5 hydrogen environments. So therefore I would get 5 peaks on my spectrum. So that's quite nice and straightforward. When answering exam questions, I do tend to do it like this because it's quite hard to write in words what you mean. So I would tend to draw out my molecule, circle my hydrogen environments, and then make sure you pop this down. You're generally going to get a mark for it if it's a 6-mark question. And then you might want to number your environments. So 1, 2, 3, 4, 5. And then you can refer to them more easily. So the hydrogens in environment 1 or H1 hydrogen, something along that line. Okay, let's look at another example. So let's look at, instead of butan 2-ol, let's look at propan 2-ol. I was being teased earlier about my very high production value videos, but hopefully they do the job. Right, so again, hopefully you can see this hydrogen on the OH is different to all the other hydrogens. There's nothing else like it. And this hydrogen here is on a carbon which is attached to an OH, which is different from all the others. Then we've got these 3 hydrogens on this CH3, but can you see that these 3 hydrogens are actually exactly the same as these 3? Because you've got some symmetry down through the molecule. So this is a CH3 attached to a CHOH, and then this side is also a CH3 attached to a CHOH. And so if I kind of keep looking along my molecule, I keep reaching the same things. So they're in the same environment. So again, it's like that thing, if you're in university halls of residence, it's like bedroom, bathroom, bedroom. So you've got symmetry. These are in the same environment. So here I've got 1, 2, 3 hydrogen environments, which gives me 3 peaks. So look out for symmetry. Okay, let's have a look at, we'll go back to our first example, and we'll have a look at some of these chemical shift values. So to do that, you need to look at your data sheet. So here is a copy of I think it's the 3rd page on the data sheet. And what you need to look at is the bottom half of this page. So the top half is about carbon-13 NMR, and I've drawn this line to split it so that you can see the top half is about carbon-13 NMR and the bottom half is about proton NMR. So you've got the scale at the bottom with the chemical shift values from 0 to 12 in this case, and each little block tells you about the type of hydrogen that will give you a peak in that region. And do be aware, these are guides, okay? So say we imagine this little block here is between 2 and 3. If you see a peak at 3.1, that doesn't necessarily mean it couldn't possibly be a hydrogen of this type. So there's some kind of professional judgment along the way. A couple of things to notice is that up the top here, this bar is for an OH and an NH. So essentially they can be anywhere, so that's not very helpful. Generally, OH hydrogens are often more down this end, I would say, but they can be potentially anywhere. And then the other thing I have in my mind, if you've got hydrogens on just a carbon that's surrounded by other carbons, so quite kind of boring hydrogens as it were, they tend to be down this end very much. So we'll look at that. One thing I want to expand on is, I think you have to be careful. I think this is a little bit misleading. So if we look, for example, at this first little bit here, it says HCr, right? So what does that actually mean? So HCr, and the H is bold. Now, so R, what they mean here is that R has to be another carbon, or it could actually be a hydrogen, but it can't be an oxygen or a nitrogen or a halogen or anything like that. And then this encompasses, it might have been handy if they'd have put HXC, because it doesn't matter how many hydrogens are attached to this carbon, they're still going to give a peak in that position. So really, this could be just one hydrogen and all the others are carbons, or it could be 2 hydrogens and 2 carbons, or it could be 3 hydrogens and 1 carbon. I guess potentially it could be CH4 as well. That would just give you the 1 peak in that position, which wouldn't be a very interesting spectrum. You probably wouldn't be using NMR to analyse it. So think of it more as HXC. Doesn't matter how many hydrogens you've got. It could be a CH, it could be a CH2, it could be a CH3. So just be aware of that. And then the other thing to know is that essentially you're looking for your best match in terms of trying to assign your chemical shift value. So if I was looking at this one, again in the exam, I would draw it out like this. So if I look at this one, I've got some hydrogens on a carbon, which is attached to a carbon, but I do notice that there's an oxygen attached to this other carbon that's next door. So I kind of have a look. I don't know if there's a chemical shift that will match that. Nope. So the closest one is just the HCr. So I think that's going to have a chemical shift of about 0.5 to about 2 roughly, using my scale. And remember this OH hydrogen, unhelpfully that's anywhere from about 0 to 12. Who knows where that's going to pop up. So this hydrogen number 2 up here is on a carbon which is also attached to an oxygen. So on my data sheet I've got HCO, and it's this H. So hydrogen's on a carbon which is directly attached to an oxygen, and that's appearing at a chemical shift of about 3 to 4.2. So that's where that's going to appear. Okay, this carbon, or these hydrogens on number 4, so these ones, again, if I look at what's next to them, they're next to just regular carbon. So this is a CH2 attached to other carbons. So that's going to be my 0.5 to 2 as well, as is this one. Because again, I've got hydrogens on a carbon which is just attached to other carbons. So it's likely that kind of we've got 3 of these peaks which are appearing in a similar position. It will be similar, they might be slightly separate. If you're near an oxygen, that usually shifts the peak a little bit towards a higher value, but they wouldn't expect you to necessarily know that. Okay, let's look at this area business. Apologies if you hear kind of drilling and things. I'm having my house torn apart apparently, so hopefully there won't be too much of that. Okay, so the ratio business is very straightforward. So all you have to do is go along and count how many hydrogens there are in each environment. So I've got 3 to 1 to 1 to 2 to 3. And it doesn't matter what order you put these numbers in, it really doesn't matter, as long as you've got the correct numbers. And so again, in exams, I tend to draw my molecule and then underneath kind of go along and do the ratios. But you could, again, illustrate that these are H1, H2, H3, H4, H5. So that's the ratio, and I just did that by counting how many hydrogens. So that means my ratio of the peak areas will be 3 to 1 to 1 to 2 to 3. So on my spectra, let me try and remember. So these, remember, were over here. So that's a kind of tallish peak. That was a bit further along, and that's only a kind of 1/3 of the area, which, remember, if they're narrow, is usually their height. This one I suspect is going to pop up over here. These are going to be kind of here-ish, so that's a 2, and then these are probably going to be over here-ish again. Okay, so you can see this spectra with the different areas of the peaks. And sometimes in the exam, they will write above each peak how many hydrogens are causing that peak, because traditionally they mark on something called an integration trace, which mathematicians will know more about than I do, which tells you, and then you actually use a ruler and measure a portion of that, but that can be a bit tricky in the exam. So sometimes, as I said, they write the number of hydrogens causing the peak above that peak. One thing to look out for, which is a bit of a clue, is if you have a benzene ring. So there's my benzene ring. Let's put a bromine on it. So remember, on each point of a benzene ring, you've got a hydrogen unless there's something else there. So how many peaks are we expecting? Well, I would tend to expect that this is hydrogen. Can you see that there's symmetry down the middle? So that's actually the same as this hydrogen. So they're the same. And this one is the same as this one because of what's next door. If I keep going round, I meet the same things. And this is another one. So I think we've got 2 and 2 and 1, but they are very, very similar. So their chemical shift values are going to be similar. So what can happen is they kind of end up giving a peak in more or less the same place. And so if ever you see a peak with 5H written above it, quite likely that it's a benzene ring, because otherwise how are you going to get 5 hydrogens which are identical? That's quite unlikely. They can't all be on the same carbon, can they? So usually 5H, especially look at the chemical shift value. So benzene ring hydrogens are kind of 6 to 8ish. So if it's somewhere between a chemical shift of 6 and 8 and 5 hydrogens, that's probably a good clue that you have a benzene ring. Another one that's unusual, or not that unusual, but it's kind of quite useful to look for, which might help you out, is if you have a peak that says it's due to 6 hydrogens and that's a very low chemical shift, so somewhere kind of around 1 or 2ish. Like, how are you going to have 6 identical hydrogens? Again, they can't all be on the same carbon, but that's probably that you've got 2 identical, remember, like we did before, CH3s. So if we have something like this, the 2 CH3s at the end are identical, and so would give us a peak caused by 6 hydrogens. So 6H, you probably got 2 CH3s. So we'll leave it there for now, and we'll come back and do splitting on another day. Hope that helps.